Now we're ready for the next portion of Chapter 17, which covers ketone bodies, which I have lovingly referred to as the Starvivores, or Acetone Strikes Back, or Return of Thiolase. So the bulk of this really has to do with the fate of acetyl-CoA, and under what conditions does it go from one pathway to a different pathway. So one possibility is through the formation of ketone bodies, and an example of ketone bodies that are biologically relevant are acetone, which is our good friend from organic chemistry, acetoacetate, which is a diketone, and D-beta hydroxybutyrate, or for those who are currently in organic chem 2, we would be calling this 3-butanoic acid. So the term ketone bodies really is a misnomer because bodies is just a historical artifact. And if you're a healthy individual, you have very, very low concentrations of ketone bodies. Okay? And so in healthy individuals, the acetone is produced in very small quantities, and does anyone know where it goes? Like what happens whenever your body has a small amount of acetone? The principal way to eliminate it from your body is actually through exhalation. And so that's why we'll talk about the fact that, for some people who are suffering from ketoacidosis, they may have acetone breath, or their breath may smell more like vinegar. The other two ketone bodies are transported in the bloodstreams to tissues, other than the liver, for use as an energy source. Okay, so muscles, kidneys, your brain, and these other tissues are able to utilize ketone bodies in very small quantities or small concentrations under certain conditions in order to get energy. Okay. However, the liver produces the ketone bodies, but it is incapable of using them for energy. And it's really important later on that you make note of the reason why this is so important. So we're going to use what we know now to answer the following questions and to look at this metabolic pathway of the formation of ketone bodies. And so, first off, you need to always keep in mind where it occurs, and with respect to beta oxidation, what tissues, things like that, why it occurs, what tissues can or cannot use the ketone bodies for energy, and why. What enzymes are involved, the biological ramifications, and what happens whenever this process goes awry. So if we just look at the beginning here, we can see that we have two acetyl-CoAs. So what's happened is your body's not getting enough glucose, and so you're going to undergo beta oxidation. But at some point in time, you're going to have an accumulation of acetyl-CoA. Okay? And so what we're going to look at now is we have an enzyme that adds two acetyl-CoAs to make an aceto-acetyl-CoA, which we've seen before. So what class or classes of enzymes can do this? Please note, it does not utilize any energy in the form of ATP, and it is not some type of redox reaction using a cofactor like NADH or FADH2. It's actually our good friend thiolase. It's the same enzyme that was utilized in beta oxidation. Okay? So hence the reason why I said the return of thiolase. Now we have acetoacetyl-CoA, and what happens here is another acetyl-CoA actually comes in and adds the acetyl group and releases one coenzyme A, which is important. So now we have this huge name for beta-hydroxy, beta-methyl-glutaril-CoA, which they usually abbreviate as HMG-CoA. So this is the beta carbon. It's beta because if we look at where the coenzyme A is located, there's the ground zero, so the alpha carbon, the beta carbon. So we have beta-hydroxy, beta-methyl-glutaril-CoA, because it does look like glutamate otherwise. So what class or classes of enzymes can do this? Well, since we are making something and it's not requiring ATP, the class of enzymes that would make the most sense for this enzyme would be the synthases. So if you're going to logically name this, you would name this one as HMG-CoA synthase. Lo and behold, voila. Okay, now that we have HMG-CoA, we need to break it down. It releases one of the acetyl-CoAs to go back through the cycle. And we have acetoacetate. So notice, essentially what we've done is we've been able to link two acetyl groups together to make acetoacetate and to release the coenzyme A's. Okay, so what class or classes of enzymes can break this type of bond? It would make sense for it to be a lyase. And so once again, using common logic, we would call this one HMG-CoA lyase. Now there are two possibilities, or I shouldn't say two possibilities, there are two things that actually happens with the acetoacetate. One is that you can get a decarboxylation, and for those of you, please know, for those of you who are currently in Organic Chem 2, and we've been talking about beta-keto acids, look what we have here. We have a beta-keto group to a carboxylic acid end, or carboxylate. So we are actually going to be able to do a decarboxylation reaction where the electrons will come down, smack to form the double bond here with the carbon, and then these two electrons will then go on in order to have the hydrogen added onto them. Okay, so what class or classes of enzymes can do this type of reaction? I'll give you a moment to think about that. That's right, it's going to be a decarboxylase reaction. So this is acetoacetate decarboxylase. Finally, another possibility is that through the use of NADH, we actually end up getting the reduction of acetoacetate to D-beta-hydroxybutyrate. So what class or classes of enzymes utilize NADH to do reduction reactions? You're right, once again, it is D-beta-hydroxybutyrate dehydrogenase. Okay, so we've already said that the acetate under normal conditions would be exhaled. So what about the hydroxybutyrate? What is the possibility here for hydroxybutyrate and how we can utilize it in order to get energy and fuel? So the tissues that can utilize hydroxybutyrate, what it does is first it takes an NAD in order to make an NADH. And of course the NADH is important because it's what's going to go on into the electron transport chain in order to synthesize ATP through oxidative phosphorylation. So what class or classes of enzymes can undergo this kind of reaction essentially as a reversal of beta-hydroxybutyrate to acetoacetate? Well, we've actually seen this one before. This is beta-hydroxybutyrate dehydrogenase. Okay. So now we have something that's different. We've got a succinyl-CoA, which where have we seen succinyl-CoA? Yes, from the citric acid cycle. We have a succinyl-CoA that's effectively transferring the coenzyme A to the the carbonyl group and releasing the succinate. So what class or classes of enzymes can undergo this type of reaction? It is a transferase. Notice it's called the beta-ketoacyl-CoA transferase. So it's a mouthful, but that's really what it's doing. Is if we look, this is a beta-keto group to an acyl group. See, beta-keto-acyl-CoA, and this is a transferase enzyme. Okay, and finally, we have acetyl-CoA, which we've seen before, and it's being broken down to acetyl-CoA using our good friend thiolase once again. So now I want to summarize what's in the good times, right? And normally what happens is, let's say everything is going well. You can break down the lipid droplets, okay, in order to make the portions of the biomolecules that are important. So, for example, you can have the fatty acids undergo beta oxidation and make acetyl-CoA. When time is good, then of course you can undergo the citric acid cycle, just like normal. However, at some point in time, you're going to start to run out of regular glucose. So what you can do is now we can scavenge from the citric acid cycle the oxaloacetate. The oxaloacetate then can be converted to glucose using gluconeogenesis. The glucose can then be exported to the brain for fuel and to the other tissues of fuel. At some point, as you start to use this up, you're going to run out of the intermediates. Then, under these conditions, the acetyl-CoA will start to accumulate. Acetyl-CoA accumulates, you can undergo ketone body formation, which then the ketone bodies can then be distributed, the acetoacetate and the hydroxybutyrate, to be energy source under these extreme circumstances for the heart, skeletal muscles, kidneys, and the brain. But it's not for the liver. So, that's been a good general review for it, but now why is this important? Okay. So the liver can produce these ketone bodies, but it lacks the enzyme of the beta-ketoacyl-CoA transferase. Since it lacks that transferase, the one that utilizes the succinyl-CoA, it cannot compete with the brain or the muscles under these conditions for energy. Because you're doing this, the only time that a healthy individual undergoes ketone body formation is whenever you really need energy and you're not getting enough of the other nutrients. Okay, so what happens is there's a very limited supply of coenzyme A in your body. This will allow, so by doing ketone body formations, you allow for the fatty acids to continually be broken down for energy, and yet you can see that it does so with minimal oxidation of the acetyl-CoA, meaning that it frees up some of the coenzyme A in order for the process to go on. Because what happens here is that citric acid cycle intermediates can be then siphoned off for gluconeogenesis. Like in particular, we're talking about oxaloacetate. We talked about how alpha-ketoglutarate can be used for these processes. And so they can be used to make additional glucose. You're going to actually start to decrease the amount of the acetyl-CoA around. Beta oxidation also will decrease, and so the ketone bodies provides this extra energy source, this oomph for the other tissues, so that way the coenzyme A is freed to remain there within the liver. Once again, this is for under the normal conditions. In the next part, in the next video, we'll talk about what happens when ketone bodies run amok. So I'm planning on trying to break these videos down of what would normally be in a lecture, so that way they're not quite so long. Stay tuned for more.